So U-substitution and trig can be it can be a bear. Okay, so you've got to really understand those trig identities, have those things handy so that you can look at them and see if they don't help you resolve some of the issues that you see here. We're going to use those as we go throughout a few of these examples. One thing I want to do is point out this right here. So the procedure is going to be the exact same, right? Find a substitution function u such that part of the integrand is a function of u and what remains is captured by du. That's just a complicated way of saying, see if you can find a function whose derivative is part of the problem, okay? So again, the same tricks apply. You know, if it's in parentheses or if it's raised to a power or under the radical, those are hints at what u should equal. Sometimes it's not as obvious, and that's what we're going to talk about here. So take a look at this problem. We want to evaluate cosine squared theta d theta, and this is a doozy. This is one that kind of jumps out at you. And it's one that I want to start with because it's a really good example of how do I know when to use u substitution and how do I know what to do. So if you use that hint that u should be the thing being raised to a power, then you would have u equal to cosine theta. Well, that implies that du is negative sine theta d theta. And the unfortunate thing is that I don't have a sine anywhere in here, right? So that begs the question, what do I do? Where do I go? One of the things that we want you to do is to use those identities. Okay, so take a look at the identities here. This is that identities page I've loaded for you. And we have an identity right here that we're going to manipulate. Okay. There is a cosine squared right here. And I want to focus on this one. So I can look at this one. There's a cosine squared there, but do you see how it employs a sine as well? So I want to focus on this guy because I only have cosines and numbers, right? So what we do is we can take this, I can move the 1 over, so I'll have the cosine of 2x plus 1, right? Because I've moved this over. And that's equal to 2 cosine squared of x. Now I can isolate cosine squared of x if I just divide all of this by 2. Uh-oh. I have a hard time writing a plus sign on a PDF. I don't know what it is. The last thing that we can do is break this thing up into the cosine of 2x over 2 plus 1 over 2. Okay, and that's what we've done in this example here. You'll notice that we've got cosine squared of theta equal to 1 plus cosine 2 theta over 2. So we're using that substitution. So now our focus is on how do we take the antiderivative of this. Okay, so these are equivalent expressions. I'm going to break this fraction up into two parts, 1/2 and the cosine of 2 theta over 2. Remember that we can break an integral like this up into the integral of 1/2 d theta plus the integral of 1/2 cosine 2 theta d theta, right? So we've got those two integrals there, and this guy's easy to work with, not a problem. What do we do with that one? Okay, so our focus is how do I take the antiderivative of 1/2 cosine 2 theta d theta? We're going to let u equal 2 theta. And here's the hint. On some of your trig derivative or your derivative tables and things like that, you'll see the integral of cosine u du. So u is the thing we're taking the cosine of, right? In this case, we have u equal to 2 theta. Du is the derivative of this, which is 2 d theta. And if I go back in and make those substitutions, I've got the integral of 1/2 cosine u. And then d theta is going to equal du over 2, right? So we're going to have not d theta, right? We're going to take that out and put du over 2. So you can see where this 1/2 and this over 2, they combine to give me a 1/4. So our resulting integral is going to look like this, 1/4 cosine u du. Let's take a look at this next slide here. So we've got the integral, so we've got the integral, right, 1/2, okay? Now, I broke mine up, and I said the integral of 1/2 d theta plus the integral of, this is going to be 1/4 cosine u du. So the integral of 1/2 d theta is just 1/2 theta. And you can see that shows up here. Now I'm going to go find the integral of 1/4 cosine u, and that's going to be 1/4 sine u plus c. And again, u was equal to 2 theta, so 1/4 sine 2 theta plus c. And you can see that is right here. So however you want to do the problem is fine. I did the problem a little bit differently than what you see here on Newton. I, again, encourage you, find that way that works for you, whatever your understanding. As long as you're getting the problem correct, you're doing it right. Okay, here's another one where it's not exactly obvious what u is equal to. So let's think about this thing. If I let u equal tan x, u equal tan x, then du is going to equal secant squared x dx. And we're close, right? We have, oh man, if I could just make that 2 a 5, I would have that du. Here's what I'm going to do. And this is not, again, I wouldn't expect that you could look at this problem and tell what to do. But would it be okay, would there be anything wrong with me rewriting this as secant to the 4th x times secant x times tangent x, okay, dx. So the reason I did this is because now if I let u equal secant x, well, the derivative of that is secant x tangent x dx. And look there, I've got secant x tangent x dx. So that's exactly what happened here. We rewrote this problem where we took out a secant, and now I have the integral of u to the 4th, right? Because u is secant. The integral of u to the 4th du, we know how to take the integral of that. We add to that exponent and put it underneath. So it's u to the 4 plus 1 over 4 plus 1. I'm just going to go back and plug in what u was. So I'm replacing u back with secant now, and I have that integral, 1/5 secant to the 5th x plus c. So here's one that's interesting, right? So we've got the integral of tangent x. I'm using some of those trig identities. I'm going to call this tangent, I'm going to call it sine x over cosine x dx, okay? So u is going to equal cosine x, and that makes du negative sine x dx. Well, now we're going to have the integral of, okay, I've got my negative, right? I'm going to replace this. I'm going to replace this with negative du. So negative du over u. And the integral of negative du over u, right? We've got that right here. It's negative natural log u, and we're going to plug that cosine back in. So we're using those trig identities to see if we can identify u and come up with something that's a little easier to take the antiderivative of. So here are some things that you can read through, just some fundamentals that might help. And this problem is very, very similar to this last problem here with cosine to the 4th. So I'm going to do one of these and let you kind of read through the other. They work basically the same way. So here I'm going to say that I'm going to rewrite this as sine times sine squared, okay? And so the reason being is we've got to figure out how to create that u du, okay? So from your trig identities, right, there, you see this guy, sine squared plus cosine squared equals 1. I can kind of manipulate that and get sine squared equals 1 minus cosine squared, okay? The reason I want to do that is because now I can create an integral that's much easier to work with. So I have the integral from 0 to power 3 of sine times 1 minus cosine squared. Well, that's a fairly easy one to do. I'm going to distribute the sine, and now I've got the integral from 0 to power 3 of sine, which is really, really basic. That's an easy one to do. And then I've got this second one over here that I've got to deal with, right? So I've got cosine being raised to a power. I'm going to let u be cosine. Excuse me, just cosine. Du is negative sine x dx, right? So we can make some substitutions right here. And this integral, this yellow one, is going to go to the integral of u squared. There we go, u squared. And I'm going to replace the sine x dx with negative du. So it's negative right here. The integral of u to the second is u to the third over 3. So we're going to have this, the second piece of this is going to be, cosine to the third x over 3, or 1/3. Now what we do is we're breaking, in the PowerPoint if you're following along, we're taking this piece right here, this first part, and evaluating this. Okay, so we're using our unit circle. Okay, the integral of sine is negative cosine. I plug in pi over 3. I subtract what I get when I plug in 0. Okay, and these values again are coming from the unit circle. So this first piece right here is going to evaluate down to 1/2. Now we went in, you and I went in, and we figured out the second half of this guy right here. We figured out that the integral of that was 1/3 cosine to the third x, right? So we've got 1/3 cosine to the third x. Now here's the thing. If you notice, okay, in the PowerPoint, we come up with these new values, 1/2 and 1. So where are those coming from? Well, if you remember, we said that u was the cosine of x. So I'm going to figure out what the cosine of 0 is, which is 1. That's based on the unit circle. I'm going to figure out the cosine of pi over 3. That's 1/2, again, based on the unit circle. When I make those substitutions, you'll notice that I finished the problem by working with only u's. So I don't have to go back and plug in that cosine. I can just finish by evaluating negative 1/2 to the third power over, parentheses, got a little bit long there. So 1/2 to the third power, and we're dividing that by 3. And we're subtracting out what we get when we plug 1 in, right? So that's 1/3. And those values are going to come out to what we have right here in the PowerPoint, okay? So there's a lot of math that just, we go from here to here and wonder, well, how on earth did that happen? So let me break that down for you. 1/2 to the third is negative 1/8 over 3. Now, if I'm dividing by 3, that's the same as multiplying by 1/3. So this first piece right here is negative 1 over 24, okay? And I'm going to subtract out what I get when I plug in 1. Well, I'm going to subtract out a negative 1/3, which is going to turn into positive 1/3. And I need to get a common denominator, so I'm going to change this 3 to a 24, which would make the top 8, right? I'm multiplying the top and bottom by 8. 8 over 24 minus 1 over 24 is 7 over 24. Okay, so again, we're plugging the 1/2 in, and it would look like this. I know that the PowerPoint skips this, and I didn't do a very good job initially of writing that down. So let me show you. We're going to have negative 1/2 to the third over 3 minus negative 1 to the third over 3, right? So it's like this right here. And this is how we set up to evaluate that, okay? Now the final answer is going to be 1/2 from the previous slide minus the 7 over 24. Okay, so you're wondering, well, why is it minus? If you recall, we had a negative in there, okay? We had this negative from our trig identity. So we had this first integral minus this second integral. And that's where that minus comes from. Again, we're going to get a common denominator, right? It's 12 over 24 minus 7 over 24. And that's 5 over 24. So I will leave this one for you to take a look at. Again, we use sort of the same thing. This one's a little easier though because we can just quickly identify that u is cosine of x. Again, u is typically the thing being raised to that power. Go in and take a look at a few of these in Newton. Let's see if we can't get you get you on the right track. I'd love to hear from you. This last problem right here is a good one. We have sine under the radical. Again, u is going to equal sine of x, okay? And du is cosine x dx. So you're able to make some pretty basic substitutions right here. The square root of u, right, du. Notice that we do change the boundaries by plugging in pi and pi over 2 into sine. That helps you out. We've got 2 more sections we're going to look at before we wind this class down. I'd love to hear from you and get some feedback on what additional resources you might need.